this lecture series of advanced data structures and algorithms, we looked into the extract min procedure of Fibonacci heaps, and from here onwards we will be looking into the potential calculation and amortized analysis of that particular operation, and we will also cover two more operations which are decrease key and delete node. So how are we going to how are we going to take that? Let us see. We have seen Fibonacci heap as a tree based data structure with some mergeable heap operations, and we have also seen the extract min, in which we are kind of deleting the minimum, then kind of we can say reconciling the whole Fibonacci heap, and that involves union operation also. Now, when we talk about the amortized analysis, and you all are aware that the amortized analysis of these Fibonacci heap operations we are taking with the help of potential functions. Let us look into the actual cost first, and then we will be looking into the potential or change into potential. So, actual cost, if we can say a Fibonacci heap has at most d of n children. So, d of n, as you can say, is actually the we are denoting the degree as d of n, and after concatenation there will be at most number of trees in the heap H plus dn minus 1 nodes on the root list, because one node in the process of extract min has been kind of deleted, we can say. So, as far as number of nodes are concerned, it is going to be T of H, which is already kind of the number of trees, plus the degree of d, or degree d of n minus 1, and linking or uniting any two trees, that we have seen that requires an order 1 operation. So, total cost of concatenation, then linking and updating the min H. So, these are the three kind of procedures which we have seen in our previous lecture as a part of your extract min, in which we need to concatenate, or which we need to unite the two trees which are of similar degree, we need to link them to the array, and then finally we need to update the min H. So, the total cost of this concatenation, linking and updating is going to be order of T of H plus D of n, and actual cost, if we talk about, is going to be order of T of H plus D of n. This is the actual cost which is denoted by C. Amortized cost which we are going to denote with the help of C hat. So, extract min is we can say if you are familiar with binomial heaps, extract min operation is quite similar to the operation which is done in binomial heap, in which let us say that A is a tree with root min H. We are going to extract this H from A, that means we are removing the root of A, and we are reinserting the remaining trees back into the root list of heap, updating the min of H during this procedure, and link the roots of equals degrees until at most one root remains each degree. And this is what precisely we did in our previous lecture for Fibonacci heaps also. So, comparing extract min operation in Fibonacci heap as well as in binomial heaps is actually of no difference, they are same. So, if we talk about the potential potential calculation of this whole data structure during this procedure of extract min, the original potential was phi h, which is equals to number of trees in H plus twice into marked node. So, phi h is equals to T of H plus 2 of m h, and if you if you are able to recall this extract min, marked nodes cannot be created by the operation, they can be only cleared. How they are going to be cleared, I will be explaining in a short while. And after all the linking, there will be at most d of n minus 1 plus 1 nodes on the root list. As I have told you, dn was the maximum degrees. So, now after the whole complete linking, after the removal of your min, which is the operation extract min, there will be at most dn minus 1 plus 1 nodes on the root list, and final potential, if we can see, is phi of h dash. H dash, you can say, is the new node, is the new tree, is equals to T of h dash plus 2 of m h dash. And now this is actually going to be lesser than or equals to. Why I am saying lesser than or equals to? Because this cannot be greater than, because we are linking the trees. If we are linking the trees and if we are clearing the marked nodes, then both the ways the total number of trees is going to be decreased certainly, or if we are clearing, then total number of marked nodes is also going to be decreased. So, finally the new potential of or we can say the final potential of the newly created your heap, which is denoted by phi of h dash, is equals to T of h dash plus 2 of m h dash less than equals to d of n plus 2 of m h. And this phi of h, when we are subtracting phi, now this is kind of, we can say, phi of h dash minus phi of h is going to be less than equals to d of n plus 2 of m h minus T of h plus 2 of m h, which is, if you can solve this expression of phi of h dash, what we have written, and phi of h, this is going to be equals to, or this expression is going to be equals to d of n minus T of h, because these are the two terms which are left after cancelling your T twice, 2 mh in the first term and 2 mh in the second term. So, that is going to be cancelled. So, phi of h dash minus phi of h is actually less than equals to d of n plus d of n minus T of h. So, this is kind of, we can say, is going to be our final potential. If we talk about the actual cost, so actual cost here, which is obviously denoted by C, is equals to order of Th plus d n. So, when we say order of, we can say this is kind of an upper bound. So, T of h plus degree of n, or we can say the d of n, that is the denotation we are, that is the we can say the term which we are giving it to. Then we have if we want to calculate the potential, or we can say the change in potential, so it comes as phi of h dash minus phi of h. We have just seen that this is less than equals to d of n minus T of h. So, amortized cost, if you can see, C hat is equals to the actual cost plus change in potential. Now, what is change in potential? Change in potential is phi of h dash minus phi of h. So, amortized cost C hat is equals to C plus phi of h dash minus phi of h, which is less than equals to order of T of h plus d of n plus d of n minus T of h. These are the expression which we have written for C, which we have just calculated actual cost, as you can see on the first line of the screen, and then we have calculated change in potential less than equals to d of n minus T of h. So, these terms we have just replaced the value of actual cost and the change in potential, and after a simple mathematical calculation we are coming to the expression which is order of dn, if you can see. So, order of dn. So, we can say the cost of which is the amortized cost is equals to order of dn, and which is nothing but equals to order of log n. What is the kind of reason, or what is the technique behind keeping the potential as, or behind having the potential as T of h plus 2 of m h, that I will be covering after completing all the operations. So, there is a reason behind that why this particular potential is being taken as a fixed potential. So, that we will be also looking into, and d of n is equals to order of log n. This expression also kind of we can say you need to hold for some time. We will be taking it after all the operations have been covered. So, amortized cost of extract min is, if we talk about, is order log n, and please recall the first lecture of this Fibonacci heaps, in which we claimed that this extract min is going to be an kind of order log n operation, and hence we have calculated this amortized cost to be equals to order of log n. Now, moving further, two of the important operations which are not among the mergeable heap operations which are left are decrease key operation and deleting a node. So, let us try to understand these operations one at a time. So, if we talk about decrease key operation as the name indicates, it decreases the value of a given key to any lower value, and if we talk about deleting a node, simply this will delete the given node. So, in decreasing a key or in this decrease key operation, the value of key is decreased to a lower value. In then the selected node is to be decreased to a particular value, let us say k, which is the value of the key lower than the present value of that node x. So, we are let us say selecting a node x, and if we are decreasing the key to k, one thing is for sure, that k is definitely lower than the current key of x, then only this decrease key operation is going to solve any reasonable purpose. Now, if we talk about decrease key, it is not only about the selecting the node to be decreased and changing its value to the new lower value. It also involves two more operations. One is a cut operation, another one is known as a cascade cut operation. So, now why do we need cut and cascade cut? So, for example, if we are going to decrease the key for a particular node x, let us say, and after decrease we realize that the parent node of x is now having higher value as that of the x keys, then this is not going to solve, or this is not going to represent the min heap property, then that x has to be cut from that particular tree and is to be attached to the root node, and this obviously is going to kind of generate, or this obviously is going to call a cascade cut operation. How this cut and cascade cut operation is going to take place, that we will see. So, first of all, we will select the node to be decreased, which is let us say x, and change its value to the new value k. If the parent, which is y, of that node x is not null, that means parent is existing, and now the key of the parent is greater than the new key of the kind of we can say the node, then we are going to call the cut x and cascading cut y subsequently. And if the key of x is smaller than the key of the min, then we need to mark x as min also, because we need to see that do we really need to update the min as well. Now, this whole procedure is going to be kind of get cleared within a short while. So, in case of cut, we will be removing x from the current position and add it to the root list. Now, here is a change, that if x is already marked, then there can be a marked node. If x is already marked, then we are going to mark it as false, that means it is not marked anymore. Now, looking into the operation of cascading cut, if the parent of y is not null, then follow the following, the parent of x is not null, here I am naming the variable as y, then follow the given steps. If y is unmarked, then mark y because it has lost children, and else call the cut y and cascade cut parent of y. So, how this is going to happen, that we will see in a short while with the help of example. So, here we have an example which says we need to decrease the value 46 to 15. Now value 46 is available in the tree rooted at 7 and in the subtree rooted at 24. Now let us say if we are kind of deleting or decreasing its key to 15. Now see what is the dilemma here. The dilemma here is the parent of 15 is 24, which is greater than this, and we are talking about a min heap. So this condition should not go here. In that situation, what are we going to do? We are going to perform a cut part which says that 24 is not equals to nil. That means the node which we are going to cut is having a parent, and now the key of the node is less than its parent, so it cannot be the child anymore. We need to cut it and we need to add it to the root list. So as you can see, we have we have cut this 15 and added to the root list, and we have marked 14. Now why we have marked 14? Because we have marked 24. So why we have marked 24? Because of the simple reason, mark means it has lost one particular child. So one child, which is 15, has been lost by 24. So that means we have kind of marked 24. So this is the kind of we can say the significance of marked nodes, which we have not seen in any of the operations yet, because whatever operations we have covered till this point was not involved marked nodes in a way we can say explicitly. Moving further, so this was kind of a simple example. We have taken kind of the newly decreased node, added to the root list, marked its parent, that is it. Now if we talk about what we can say is cascade cut. So cascade cut involves cascade, as you understand that it is kind of one of the operations which is result of calling the operation in a we can say step by step, level by level manner. So here let us see, we have a tree, we have that particular tree which is having 15, 7, 18 and 38 are in the root list. And now here if we talk about the marked nodes, we have 18 as a marked node, we have 39 as a marked node, 24 and 26 also. Now we are going to decrease the value of 35 to 5. Now please notice the position of 35. The position of 35 is the children of 26. The 26 here is marked, and the parent of 26, which is 24, the 24 here is also marked. And let us say we decrease the value of 35 to 5, then the decreased value cannot stand here, because 5 is now less than the parent of its own, which is 26. So this 5 has to be kind of gone, and the normal procedure says we need to mark 26, but here the situation is 26 is already marked. So what are we going to do next? So here if you can see, 26 is not nil, 5 obviously, which is the new key, is less than its parent. We need to cut it, add it to the root list. What is left? The left is the marking of 26, but 26 is already marked. That means again we need to call cut, which is now we are calling as cascade cut. So this is a resultant move of calling cut at the repeated levels, which I was trying to explain. So now the flow goes to cut and then cascade cut. So we are going to cut 26. If we are going to cut 26, we are going to add it to the root list and mark it as false. That means the earlier it was kind of marked, now it is non-marked. So here the situation of the min heap, if you can see, or the Fibonacci heap, if you can see. So we have 15, we have 5, these are the two keys which we have just cut. Then we have 26, which is a result of cascade cut. And now if we talk about the marked nodes, so marked node here which are remaining is 18, 39 and 24. 26 is not a marked node anymore, because it was already we can say it was already marked, and the moment it has lost its children 5, then it is to be shifted to the non-marked nodes or mark it as false, we can say. So, here this is one operation which is kind of we can say creating the marked nodes also. 24 has been created as marked node or has been marked as the result of the operation cut, and 26 which was already marked is now changed to has been changed marked to false because of the resultant because of the result of casket cut. So, what I am trying to say here is this is the operation which is involved in kind of creation and destruction of marked nodes or creation and destruction of marks on the node, we can say precisely. Now, 24 if we talk about here, if you can see 24 is already marked and 24 have just lost its one of the children, which is 26, and after losing the children we need to mark the nodes. But if the node is already marked, then we need to remove it from its original position, add it to the root list after deleting its marked. So, if you can see 24, that is also a result of cascade cut. 24 was also marked. So, again if we call cut and cascade cut, then these operations are going to result in this tree below. So, earlier 35 was changed to 5, cut it from the root list, 26 was marked, then cut it from the root list, 24 was also marked, then cut it from the root list, and the mark of 26 and 24 have been changed. The only marked nodes which are available now in the we can say a tree or in the Fibonacci heap are 18 and 39, the two marked nodes. So, this is what happening when we try to do this cut and cascade cut. But one thing which is remaining here in this tree is we still need to update the min node, because 7 is not min anymore. We need to shift our min to 5 because 5 is less than 7. So, finally, the final structure of the tree, if you can see, is something like this. 5 is being pointed as the min of this Fibonacci heap, and that with its two marked nodes which are remaining are 18 and 39. Here is the new and the final structure of this tree after all this cut and cascade cut operations, which are kind of the result of, we can say, decrease key operations. So, now the operation which is remaining is deleting a node, and also we need to look into the potential change in potential or amortized analysis of the operations of decrease key and delete a node. So, before going into the amortized analysis of the decrease key, let me cover deletion of node first, and then we will be covering the amortized analysis for both the operations together, because this deletion of node is actually kind of, we can say, related to some of the procedures which we have seen earlier. So, deletion of node is going to make use of decrease key and extract min operations. So, that is why I have not taken the decrease key amortized analysis as of now. I will be taking it after completion of this deleting a node. So, what are the steps to be followed while deleting a node? Let us say we have the node which is to be deleted, let us say k is the node which is kind of to be deleted. We need to apply the decrease key operation to decrease the value of k to the lowest possible value. What could be a lowest possible value? The lowest possible value here is minus infinity. So, we are going to apply the decrease key operation, and after decrease key operation we will be taking extract min operation in order to remove this node. So, basically what I can say here is that node deletion is going to be a combination of two operations. One is a decrease key operation, another one is an extract min operation. So, now complexities, as we can see, the insertion we have done is order 1, finding min kind of looking for min is any case order 1, union is order 1 because there was no change in potential that we have seen. Extract min we have seen in detail, that is order log n. What we are left with is the operation analysis or amortized analysis of decrease key, which is order 1, and then delete a node, which is going to be order log n. So, here if you can see in this lecture, we have started for a new operation, which is the operation of decrease key. We have also seen the operation of deletion of node, which involves decrease key and extract min, and at the starting of the lecture we have also seen the amortized analysis of extract min. In our upcoming lectures we will be looking into the amortized analysis of whatever operations we are left with, which are actually kind of not covered in this lecture because of paucity of time. We will be covering the amortized analysis of decrease key and delete node, and we will also be looking into some of the nuances that why these are known as Fibonacci heaps and what is the rationale behind taking T of h plus 2 of mh as the potential function for this Fibonacci heaps. That is all from my side for this lecture. Here is a list of references which is being used for the preparation of lecture. I hope you have enjoyed one. I will see you in the next. Till then, take care. Goodbye.